All right, so this is the video I was really looking forward to making when I started thinking about making instructional videos. The phase video had to come first because there's a lot that I'm going to be uh, talking about that relates to phase, and I wanted to make sure that was fully understood before I got into this because I think it'll be much more appreciated with that full grasp of phase. Now, I didn't pick this GIF because it was, just for fun. It actually is very useful to begin the conversation of uh, what a wave is. So we all know waves at stadiums, and we've seen them go fast around the stadium. We've seen them go slow around the stadium. We've seen the width of the wave be narrow, and we've seen it be wide before. And what you want to get from that is you'd know sort of intuitively from the wave that the speed of the people, individual people, do not define the speed of the wave through people. What defines the speed of the wave is how fast the the most people who are standing, where the center of all people, where the most people are standing, the center of that, you could think of that as the peak of the wave. And unlike crowd waves, the speed of sound is always the same speed. Well, for most practical purposes in audio engineering, you can consider it the same speed all the time. The changes in speed will be practically insignificant, but I guess they do change with temperature and pressure and things like that. But for the most part, you can assume it's the same speed. But what you want to get from this mostly is the fact that the particles of air don't define the speed of sound. And this is a representation more like how actual sound travels through the air. And you can see this one particle of air here. You imagine this as being like an ultralight feather, a feather that has no mass, that's just sort of floating there. It is just moving back and forth just a little bit, but it creates this density region of the particles around it. And one thing you'll want to notice is the fastest the particle is moving is always when it's in its center, where it started. It's always when it's moving the fastest. And that is also where the highest pressure is. And that is the very fundamental thing that everyone should know is the speed of the particle dictates how much pressure it creates. And that's true with the speaker. The speaker diaphragm is the highest pressure that comes out of it. The peak of the sound wave that comes out of it is always going to be when the diaphragm's moving its fastest. And the diaphragm's moving its fastest when it's at the center. It's actually stopped on either side as it changes directions. So it has the lowest speed. So both the peak of the wave and the middle of the wave, where it's the lowest pressure, is when it's in the middle. So both the highest pressure and lowest pressure happen when that particle is right where it started. And that's when it's moving its fastest. And here's just a more elaborate diagram. And just have you look at this for a little while. And so now I'm going to get into the concept of a diaphragm. And I love this GIF. I'm so happy I found it because it's got a diaphragm and it's going in it has two different wavelengths. And you can see the waves are traveling at the same speed, but it's just that this is oscillating more quickly. And the maximum speed, you can see pressure here. The maximum speed of the diaphragm matches the pressure exactly. So when it's moving back at its fastest, it's at the lowest pressure. When it's moving forward at its fastest, it's the highest pressure. But we know that the speakers are moved by the electromagnet, the voice coil, the interaction with the voice coil with the solid magnet. But the thing about it is we're feeding voltage into this. And when you apply a voltage to a coil, it creates a force. So the electrical signal is what dictates force. But remember, the sound pressure comes from speed. Now there's a phase relationship between speed, and, well, position, I should say, and pressure. And we'll get to speed here in a moment, but this diagram is very similar to the other one. And what I want to point out here is what's really interesting. You see how that arrow turns around? And that's because velocity is a vector, and position or displacement is scalar. And that's why this always has its base at 0, and that's always that turns around when it goes in a different direction. Oh, let's reset this. So the reason I'm bringing this up is I was talking about electrical force. So electrical voltage creates force. It doesn't create pressure. Now let's do something normal, like put a refrigerator on a skateboard like we always do. And so the first part of an audio signal is let's just do the positive part of the audio signal. So I'll go just do the positive part, and then I'll go down to 0 again. Oops. Now look, its maximum speed is when I stopped, and it just keeps going. So now I'll try to reverse that, and I'll get to the other side, and I'll go, 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 and bring it back to 0. Maximum speed, 6.3. Maximum speed is always achieved when acceleration is 0, when I'm giving it no force. So let's do that again. So I'll try to actually make a wave out of this. Let's see if I can. So I'll just keep going, and so I'll try to be as smooth as possible so that my wave is always doing kind of what a wave does. And sort of look at what's happening here. The maximum speed is always when I cross. But speakers have something else going on inside them, don't they? Before I get to that, I should point out that this is all intuitive to us because of punch balloons. And you can see how the maximum force that we're applying on the punch balloon is when it's all the way out here. When its velocity is 0 is when it has the maximum force placed upon it. And when there's no force placed upon it is when it's at its maximum speed. In between, when you're pulling it back and pushing it forward, is where its maximum speed is. And here's another illustration of that. Acceleration is what you get when you apply force to something. So you can think of the acceleration is always going to be completely in phase with force. This could be considered force. Just replace acceleration with force, and it would be exactly the same. You can see the phase shift of velocity, 90 degrees off. And then S is another way of describing displacement. And so you can see displacement is 180 degrees from the phase of the force or the acceleration. And this is just pure math. This isn't what happens in a speaker. This doesn't require any mass. This is just pure math that has these phase relationships. And look, it's just kind of neat. It just 90, 90, 90 from one to the other. But that's what I was going to get to, but I got a little bit ahead of myself. Speakers aren't just a mass by itself. They're held back, and they need to be held back, or else the speaker would throw itself right out of the cabinet. So here's what it's really like. So this is the diaphragm, and if I pick it up and I let go, this is just a weight on a spring. But a speaker driver actually has a lot of spring to it, but it's dampened. It's dampened more than this because when it moves, it creates sound waves, and those sound waves take away energy from the movement of the speaker. But I want to show you this because you see the difference in phase from its position and speed. And even when I push it out really far and let it go and I get these high amplitudes, you can see the frequency is the same. It's just that the amplitude goes down with that one little tiny impulse of energy that I gave it. And this is basically what you call the impulse response. An impulse response is not a term that's isolated to audio engineering. This is across a wide variety of systems in engineering is the concept of impulse response. Here's just another diagram kind of just showing what happens in a dampened system. And anyone who's into audio engineering and has looked at impulse response diagrams, they're very similar to this. It looks just like it, basically. And even if you had a perfect sound system that itself did not have any resonance that happened after you gave it an impulse, the environment that a sound system is in will have echoes, and those echoes will come back. So you can think of the environment as resonating, and the environment has its own impulse response. And this is all taken into account when you set up professional sound systems, or should be. And this is also why setting up a sound system outside is a completely different thing is setting it up inside. There's going to be different resonances, and this sort of feedback that you get has to be accounted for, and it affects phase. And there are ways that you can address this. You can measure for it, and you can try to correct for it. You can't correct for it perfectly. No sound system is perfect, but you can make it sound way better than you ever thought it possible if you take a great deal of care and measure the system, see how all of these forces are interacting, and understand how they're interacting at a fundamental level. And then you can use your knowledge to make the impulse response as accurate, as close to the original signal as possible. Now, I'm really happy I found this. This is probably the most accurate representation of an actual speaker that I can think of. And what you have to imagine here is this ball in the middle that I'll be holding on to. Imagine that is just my way of creating voltage. And the longer I stretch this spring on either side here, it's the highest voltage. So the stretch of the spring is the highest voltage, which will correlate to the highest amount of force. And then the two dots on either side will be the either side of the diaphragm. So this is actually the movement of the speaker. And then this is the surround that's pulling the speaker back into place. So I'll just bring it up and let go. And when I let go, it sort of has both the velocity. Well, hold on. I have ball one velocity and ball two velocity. Okay, so ball two is the middle one, and ball one is this one. So ball one and three are basically the same. So what I want to show you is when I let go, it sort of has its own resonant frequency. And that's important. All speakers have their own resonant frequency because their suspension pulls in the back and they have mass. So what I'll do is I'll put a sine wave through this lower than the resonant frequency. And you'll see, look, it wants the speed, the green value. It's really hard for me to create basically a sound pressure wave, a velocity wave that is lower than its resonant frequency. It keeps wanting to pull me back up. It wants to vibrate faster than that. So even though I try to create this long wave, it has a real trouble doing it. Now, this is very exaggerated, but this does happen in speakers because the spider keeps, or the suspension of the speaker keeps trying to pull it back. And even when I pull it up, it's like they don't like a ton of voltage here, and it's not pushing it out very far, like a ton of voltage to get it up that high. But look what happens when I try to hit the resonant frequency. So I can put very little input into it, and the diaphragm's going just almost as far as it was when I had to pull the voltage way up. And this is what happens. If you have an input signal and it's at the resonant frequency of the speaker in the cabinet, you can really throw that cone. And look at the velocity is really high, and it takes very little energy. Very little energy. I'm not moving it very far. But then let's see what happens when I try to go faster. I try to go faster, it also tries to stay at its resonant frequency. It doesn't want to vibrate faster than that. It does. You can kind of see like those small bits of higher frequency that come through every now and then, but it really wants to restore it. Now, this is this is highly exaggerated, but it is what I want to show you here is just how the input and the output are not lined up there's phase differences. There's phase differences that are different at different frequencies. There is differences in how much volume you get out based on the frequency you put in, based on the resonance of the system. And so even if you send a perfectly equalized signal to a speaker, just all of these things come into play where it's just not going to come out the same. And uh, that, like I said, is all possible to measure. And for the most part, there are ways you can correct for it. Now, I have two more things that I want to show you real quick. And I'm so happy I found this because this is really going to sort of help you wrap your head around what's going on inside the voice coil. So this is actually you can think of this as the output of the amplifier, and I can increase the frequency. And so you can see it's just wiggling back and forth, and you can see how these electrons, they're not even moving that far, but they're just moving. And if I lower the wavelength or increase the wavelength, lower the frequency, look at how much further they're moving to create that, because they have to keep creating that magnetic flux. So they have to keep pushing through it. Another thing to note is this B right here is the magnetic field strength. And when is it at its maximum field strength? It's at its maximum field strength when the voltage is at its highest and the electrons are moving their fastest. And that should be pretty intuitive, right? But this magnetic field, the highest magnetic field you're creating, what does that translate to? That translates to force. So the highest voltage means the highest amount of force the voice coil is pushing on the diaphragm with. And now lastly, best for last here, this is, I don't have a battery here. It's just a coil and a magnet, and I'm going to move it. Now you see the electrons, like before, they're not moving very much. And if I go slow, they move the same amount if I go slow versus if I go fast. But if I go fast, I create a higher voltage. Now this is happening inside a speaker, even though we are using voltage to move the diaphragm. The fact that the diaphragm is moving also creates electricity, and it feeds back into the system. So as the speaker is moving, depending on the speed of the diaphragm, and remember, speed is not in phase with force, so you have the speed creating an electromagnetic force that is pushing back against the amplifier, and this is perceived as a change in impedance, electrical impedance. So even though you can take a voltmeter and you can measure the impedance of a speaker, that impedance is absolutely not the impedance that it has throughout its whole operating spectrum. And at its resonant frequency, it is basically getting back electricity. That the most electricity it ever gets back from the system is at the resonant frequency that I showed you earlier. So not only is it easier to throw the system back and forth, it just also happens to correlate with the maximum speed that you achieve will push back on the amplifier. And what that means is the amplifier is using less energy because it has a higher impedance. And so the current is low. And if you have a low current, but you're getting high movement from the speaker, that means that you have more efficiency. You're using less power to move the diaphragm. It's much, much easier to create that change, that change in speed with the least amount of power when you're at the resonant frequency. And so, like I said before, if you give a speaker, a totally equalized signal, what comes out is almost certainly not going to be equalized unless you do a lot of engineering and correct for it. All right, hope that wasn't too long, guys. Hope this was really fun for you. I had a lot of fun making this. And then my next video, I'm going to get more into what's happening inside the electrically, and what also happens when we have stuff like ports in the speaker, what happens when you have a whole bunch of speakers together and they start pushing on each other. So I'm hoping to make a video like that next. All right, cheers.